So just looking into the investigation for the area under a curve, and we're looking at this function here. So we're looking at whether our definite integrals can always be interpreted as an area. So we find, the first question asks us to find 0 over 1, the integral from 0 to 1 of x cubed dx. And we should, this one's simple enough to find. We find this particular answer here gives us the integral of x cubed dx will equal the definite integral of x to the 4 over 4 between 0 and 1. Now, in this particular notation, this means here that we're going to have 1 to the power of 4 over 4 minus 0 to the power of 4 over 4. So this area is going to equal 1/4 units squared. Okay, and if we do the graph, we would find that as well. Now, this second integral here, we've got, so let's look at this one. It's from -1 to 1 of x cubed dx. And so we've done our integral before. We know that this is going to be the definite integral of x to the power of 4 over 4. But now we've got a lower bound of -1 and an upper bound of 1. When we put these values in, we're going to get 1 to the power of 4 over 4 minus -1 to the power of 4 over 4. And that is going to equal 1/4, because 1 to the power of 4 is 1, and then -1 to the power of 4 is 1, but we have take 1, so it's going to end up being 1/4 take 1/4, which equals 0. Okay, so that means that we're looking at this integral here gives us 0, whereas this one before gave us an area. All right, so the next thing here, use a graph and explain the areas here. So if we quickly sketch up a graph, now this will be a rough sketch. We got y, and then we got our x-axis. We should know that this function here is, now I'm going to have to draw this a little bit rough. It looks like this. This is usually how it is, and it goes through a coordinate 1, 1. Actually, I might try and draw it just a little bit neater because it'll make our drawing a little bit better. If I can get this to curve for me. There we go. Let's just pull that in. Well, imagine that's 0.11 there. Okay, now this shape isn't quite right, and so we will deal with that in a sec, but there we go. We've got a shape there. We picked this point here as 1, 1, and we'll move that out, something like that. Okay, now, the reason I've done this is because if we imagine on this function that this is our 1, so this would have the coordinate of 1 and 1, and then we'd have pure symmetry. This function here is y equals x cubed, if you remember, not the, so we're looking at that, the area for that between the curve, and we've got here that this area here equals 1/4 of a unit. Now, with my poor drawing, it looks like a half, but it's this value here. And when we do the same out the other side, we almost end up with, well, that 1/4 of a unit. Now, it looks like this area here is the negative. So this is like area 1, which we will call here, let's use the navy blue. So this is area 1, and then we have this area 2, which is like a negative value that takes away from our integral. So it then asks us to find the integral from -1 to 0 of the same function and explain the negative answer. Well, we've pretty well explained that already. We're actually going to be looking at this area here. It's below the function here. So we're going to be looking at the integral of -1 to 0 of x cubed dx, and keep that in the light blue, which Okay, so this here, again, we've got x to the 4 over 4, and now we've got a top of 0, and then we've got -1 here, which means our next step here is 0 to the power of 4 is our upper bound, and then we've got in here minus, and then we've got -1 to the power of 4 over 4. And this is going to give us 0, and then 1/4, and minus 1/4. We've got an area of -1/4, which it looks, so it's sort of telling us that that function there is under. So we'll keep going here. So we've got that area there. So then we've got show that the integral between -1 and 0 of x cubed dx, have I done that right, plus 0 to 1. So we're pretty much looking at those individual components and seeing whether they add up. So this here added up to 0 here. This one was the bit we did in part 1, and that was 1/4 of a unit. And then this one here was -1/4. So if we put them together, they cancel each other out. And by the symmetry of the function, we should see that anyway. Find 0 to -1 and interpret its meaning. So this, we're looking at like a lower bound to an upper bound here. So if we do this particular one, we've got x to the 4 over 4, and then we've got 0, -1. This means we're going to do -1 to the 1/4 over 4 minus 0 over 4 is our lower bound. So this is just going to equal 1/4. And it's giving us the area between this one, but it's actually almost interesting because we've actually seen this before where, like, usually this x bound, the lower bound is the lower number, but we've seen previously that our properties of a, b, f of x dx will equal the negative of b, a, f of x, so dx. So this looks like if we flip the bounds, we can change this negative here to a positive if we flip the way they're done around. So yeah, interesting. So then it says if f of x is less than equal to 0. So this is meaning if our function, I'm just going to draw in light blue, which I don't usually do, just to show you that we're doing it. So we're looking at here our function. I've put that in the wrong spot. We want to move that up. So this is the x-axis here. Okay, we're looking at a function down here now. So if we've got a function here, y equals f of x, as we've seen above, the moment the function is below the x-axis, we end up with these negative areas, and you can't have a negative area. So how do we change that? Well, we should be thinking along this and think, well, if we multiply it by -1, chances are we're going to get the correct thing here. So the area of this value here, a, b, this shaded in space, the area here should be the negative integral. So if we take the integral of this, of f of x dx between a and b, it would equal the correct area, or so that's one, or we could do the integral from b to a, f of x dx. Now the next one here, evaluate our area interpretation. So here I've got this thing here is 1 square plus this. So I'm just going to break it up so we can sort of see it. So this looks like it's 1.5. This looks like it's 3. This looks like 1 plus, what this would be 2. This here would be 1.5. This would be 3. This would be 2.5. And this next one would be 2. Okay, so I've just worked out those areas because depending on the integral here, so we're looking at finding integrals from areas. So this one, 0 to 3, we would expect that to be 5, 6.5. So I'm just going to write that equals 6.5. So let's highlight. Oh, we're going to have overlaps here, I think. So let's not highlight. But you can see I've just added 2, 3, 1.5. This next one here, 3 to 7, is this point 3 all the way to 7 here. And so we would see that is equal to, maybe I should write these out a little bit more. I'll do it this one. So we've got 1.5 plus 3 plus 2.5 plus 2, but these are all negatives. So let's get rid of that equal sign. We're going to put a bracket around this thing, give it a negative. And this would equal negative 2 plus 3 is 5, plus 2 is 7.5, plus a half is 8, plus 1 is 9. So negative 9 there. All right, the integral between 2 and 4. So we're looking at here between 2 and 4. This would be 0 because of the symmetry. We've got positive 1.5 area here, negative 1.5 area. So this would be 1.5 minus 1.5 equals 0. And then this next one, 0 to 7, we would be looking at these two integrals here. This is our positive area, this is our negative area. And so we would have, I might even write this in section 0 to 3 because that was the bit on top, f of x dx plus the integral from 3 to 7 of fx dx, and this, or cramming this in the bottom here, 6.5 plus negative 9 is going to give us an integral of negative 2.5. Cool. Now, last one here, we're doing the same thing for a function, but it's got circles in it. So we're looking at this area in here. I'm just going to calculate the areas first. It makes life easier. This is going to be pi r squared. Okay, but r is 2. So we're going to go pi 2 squared, and that's going to be over 2 because it's half a circle. This one here is going to be pi 1 squared over 2. This area here will be 4 units. And so the integrals here, 0 to 4, it asks us, oh, I'm going to change to black just so the notes look better for us when we look at these. So the integral from 0 to 4 of f of x dx, that's going to be equal to, as we see up top, it's going to be pi on 4 pi on 2, which is going to be 2 pi. Okay, 4 to 6 is our next one. So let's quickly be the integral from 4 to 6, fx dx. And you'll notice it's continuous on that interval. It's the bit between it that we see, oh, I guess you count it as continuous because it runs there. And this is 4 units. It's not units, sorry, because we're taking an integral, we're not finding an area. C, we've got 6 to 8, integral of 6 to 8 fx dx, and this is going to equal pi on 2, and that's because this is, I'm worried I'm going too quick, pi times 1 squared on 2, which equals pi on 2. And I've just used area formulas there for a circle. And then our last one, D here, we've got the integral of 0 to 8 f of x dx. I'm running out of room here, so I'm going to have to just be a little bit cheeky. So this is, we're going to add this integral here with this integral here with this integral here. These two are positives because the areas are above. I've actually stuffed up here. This should be a negative because it's below the axis. So we're going to have 2 pi minus 4 plus pi on 2, which is going to equal 2, actually no, let's change it. So 2 pi is going to be 4 pi on 2. It's going to be 5 pi on 2 minus 4. And that's it. Thanks, guys.